In this video, we will derive the Newton-Raphson method, which is an iterative numerical procedure for finding the root of a nonlinear equation. Consider a function y equals f of x plotted in the xy plane, and suppose we want to find the value of x for which the function is 0, i.e. the point where it crosses the x-axis, what we call the root of the function. The Newton-Raphson method takes advantage of knowledge about the gradient of the curve, providing an efficient iterative method for finding the root. Let's consider a point on the curve some distance away from the root with the x-coordinate x0, and let's look at the tangent to the curve at that point. Provided that f is differentiable, the gradient of this tangent will be f' of x0. Now let us project along the tangent towards the x-axis and denote the point of intersection with the x-axis as x1. Provided we aren't too far away from the root, in particular that the curve doesn't have a turning point between a and the root, then x1 will be closer to the root than x0. The 2 points on the x-axis and a form a right-angled triangle, shown shaded in grey here. The height of this triangle is of course the function value f of x0. Let us denote the distance between x0 and x1 as delta x. Then x1 can be written x0 minus delta x. Looking at our triangle, we can see that the gradient can be expressed as f of x0 over delta x. Thus, we have f' of x0 equals f of x0 over delta x. Rearranging this gives delta x equals f of x0 over f' of x0. Now, we know that x1 equals x0 minus delta x. Thus, x1 equals x0 minus f of x0 over f' of x0. Now we can find new values of the function and its derivative at x1 and repeat the procedure. We thus project to a new point x2 on the x-axis, and we have x2 equals x1 minus f of x1 over f' of x1. We can keep repeating this procedure, moving closer to the root at each iteration. We write the general form for an iteration as xj plus 1 equals xj minus f of xj over f' of xj. Okay, so let's look at an example. Consider a weir described by the equation q equals alpha h to the 3 over 2. We want to find the depth h measured for a discharge q of 3.2 meters cubed per second. Well, the first thing we need to do is generate an equation with 0 on the right-hand side to solve. In this case, discharge is 3.2, thus the equation will be 0.9 h to the 3 over 2 minus 3.2 equals 0. To apply the Newton-Raphson method, we need to generate a function that's 0 for our required value, which in this case is f of h equals alpha h to the 3 over 2 minus 3.2. We can now apply the iterative formula we derived to find the root of the function. It's often useful to have a look at the function before we start, as this helps us make good choices about an initial value to use. Here we see a graph of the function for values of h between 0 and 4. In fact, we can see that this function is well behaved in that there are no turning points we need to worry about, so any initial value should be fine. Okay, so first we differentiate f, giving f' of h equals 3 over 2 times 0.9 h to the power of a half, which is 1.35 h to the half. The Newton-Raphson update formula in this case is hj plus 1 equals hj minus f of hj over f' of hj, which is hj minus 0.9 hj to the 3 over 2 minus 3.2 over 1.35 hj to the half. Taking h0 to be 3, we get these values for f of h0 and f dashed of h0. Applying the Newton-Raphson formula gives h1 equals 2.368534. We now calculate f of h1 and f dashed of h1, giving these values, and substitute again into the formula to give h2 equals 2.329709. We keep repeating this procedure until we are happy the value of h is not changing from one iteration to the next, and we choose what degree of accuracy we want in advance, which then tells us when we have done enough iterations. In the table shown here, I have performed 2 more iterations, and we can see that by iteration 4, the estimate of the root isn't changing. However, we should note that this particular calculation has rounded everything to 6 decimal places, and the result will be influenced by this. The steps will be slightly different with a higher degree of accuracy or a lower degree of accuracy. You might like to try this as an exercise. It's quite straightforward to set up in a spreadsheet or by writing some simple code. In this next example, we have the function f of x equals 2x to the fifth minus x squared minus 5. Now, unless we look, we don't know if this function has more than one root, thus it's worth having a look at it first. Here we see the function plotted for values of x between minus 3 and 3. It certainly looks as if there's only one root, but it's worth zooming in a little to get a better idea of where that root is. Plotting it between minus 1.5 and 1.5, we can see much more clearly that it has a single root. This also provides us with an obvious point at which to start. We can take, for example, x equals 1. First, we need to calculate the derivative. We have f dashed of x equals 10x to the power of 4 minus 2x. Thus, our Newton-Raphson formula is xj minus 2xj to the fifth minus xj squared minus 5 over 10xj to the fourth minus 2xj. Here are the results obtained using a spreadsheet with a start value of 1. We see here that the first step actually overshoots to the point x equals 1.5, and after that we move in quickly towards the root. We could of course have taken 1.5 as our start point, and we wouldn't observe this behaviour. What happens if we start further away, say at minus 1? Here we can see that the first few iterations take us quite far from the root, but it does converge eventually. If you set this up in a spreadsheet, you can play around with different start points and see how the method behaves, which I recommend as another exercise. It's worth noting that in this case, taking the initial value to be 0 is not possible, as this function has a 0 gradient at x equals 0, meaning that we can't use the update formula. Now let's consider an example that is less straightforward. We have the function f of x equals x cubed plus 3x squared minus 2x plus 1. If we look at the function, we can see that there is indeed only one root, but that there are 2 turning points. This can cause problems since we are using the gradient to send us in the right direction. Let's examine this. First, we find the derivative of the function, which is 3x squared plus 6x minus 2, giving us the Newton-Raphson formula xj minus xj cubed plus 3xj squared minus 2xj plus 1 over 3xj squared plus 6xj minus 2. If we take a well-chosen starting value, say x equals minus 4, then this converges as we would expect. The table shown here shows the result of 5 iterations. However, if we start, for example, at x equals 0, we find that the formula just iterates between the two values x equals 0 and x equals 0.5 and never converges. We get similar results for a start point of x equals -1. After the first iteration, we are stuck in the same loop, which is associated with the minimum of the function between 0 and 1. Further away from the root, functions like this can exhibit other problems. Thus, for example, if we take x equals 5 as the start point, we get these results. We can see the numbers jumping around wildly as we shoot off in different directions at each iteration. Interestingly, in this particular case, it does eventually converge after 62 iterations, but there are cases where it doesn't. These examples illustrate why it is often worth looking before starting the procedure at the behavior of the function. If we make a good choice of start point, the procedure will converge. Of course, if we automate the procedure and we don't know much about the function, we can try different start points if we see this sort of behavior, but it's much better to make informed choices, as then you benefit from the quick convergence offered by this method. As a final exercise, try coding up this example or setting it up in a spreadsheet and look at how the method behaves for different start values.